Every single time you log into Netflix or, check your bank balance online or even just swipe your student ID here at Tarleton, what's really happening, it isn't magic, right? It's actually, at its core, a really complex, carefully structured conversation with a database. The whole digital world doesn't run on smoke and mirrors. It runs on this kind of meticulously designed, structured data.
Absolutely. And if that underlying structure, that database schema, if it's poorly designed, well, the whole thing can just collapse. You end up with chaos, inconsistent data, massive costs for the organization. It's a huge problem. So welcome to the Deep Dive. Today, we're really tackling a critical mission, and it's tailored especially for you, particularly if you're in BCIS 4301 in the Dr. Sampak College of Business.
Yeah, our focus today is squarely on that essential, really foundational phase of database theory. We're talking about moaning from that high-level conceptual idea, that spark of a business need, all the way to a structured working relational schema, the kind that's ready for actual SQL implementation. This is really the heart of the study of the design, development, and implementation of databases with emphasis on the relational model.
Exactly. And that ability, that skill to take these abstract requirements and turn them into something concrete, something accurate, secure, these relational tables, that is the foundational skill. It's what guarantees data integrity, period. And for you, as future business leaders, mastering this conceptual to logical conversion, it's non-negotiable. It really is the architectural blueprint for, well, any modern organization's digital backbone. This directly hits knowledge outcome 1, explaining the essential role of robust database design in modern organizations.
Okay, so we've got quite a journey planned for today. We're going to move from sort of the philosophical side, conceptual design, different modeling notations, spontaneously. Then we'll walk through a pretty rigorous 7-step mapping algorithm step by step. And then we'll get right down to the nuts and bolts, things like foreign key constraints, optimization trade-offs. We really appreciate you tuning in. If this content seems useful, please just take a second, hit that follow button, maybe share this deep dive with a classmate, and definitely check the episode description. We've put links in there to all the comprehensive resources we're referencing today. Okay, let's start unpacking this journey. It begins, interestingly, not with code, but really with thought. Right, the conceptual design phase. At this stage, we aren't worried about, are we using Oracle or MySQL? What operating system? None of that matters yet. We're purely in the high-level design space, figuring out the absolute what information must be captured.
That's absolutely key. Conceptual design is fundamentally technology agnostic. It's all about defining that conceptual schema. And the mission here is kind of threefold. First, figure out the entities and relationships that matter, what we often call the mini-world. Second, define exactly what information, what details about them need to be stored. And third, critically, define the constraints, the business rules. What must hold true for that data? Because if we mess this part up, well, no amount of fancy SQL later on is going to save us.
Right. And the main language, the visual language we use to represent this conceptual design, that's the entity relationship diagram, the ERD. But before we can even start drawing those diamonds and rectangles and lines, we really have to nail down the core building blocks. And their precise sort of academic definitions that start super basic. Entity, entity type, and entity set. What's the difference?
Okay, so an entity that's a specific individual real-world object, something with independent existence. Think like Patricia Jones, the individual employee. Yeah. Or maybe TT1000, that specific piece of equipment. It's the instance. An entity type, on the other hand, that's the collection, or maybe better, the definition of objects that all share the same essential attributes. Things like employee or equipment. It's like the template or the blueprint for the entities.
Okay, so if employee is the template, what's the entity set then?
The entity set is more dynamic. It's the actual collection of all employee entities that exist in the database at any specific point in time. So if we hired 100 new people today, the employee entity set just grew by 100 entities. It's the current snapshot of the data, you could say. And of course, entities are described by attributes. These are just the descriptive properties like name, salary, hire, date. Crucially, though, every attribute has to stick to a domain. The domain defines the set of permitted values. Is it an integer, a string, a specific date format, maybe within a certain range?
Got it. Now, let's talk about the concept that really brings order to this mini-world. Keys. We absolutely need a way to uniquely identify every single instance of an entity type, right? So what are the different key types we need to identify during this conceptual phase?
Right. Keys are fundamental for uniqueness. We need to think about a sort of hierarchy of uniqueness. The broadest definition is the superkey. A superkey is simply any set of one or more attributes whose values, when you take them together, guarantee unique identification for each entity. It works for uniqueness, absolutely, but it often contains redundant attributes. Attributes you don't strictly need for that uniqueness.
Okay, but wait a minute. Why wouldn't we just use the superkey if it guarantees uniqueness and maybe having more attributes feels safer? Why does the database care about being minimal?
Good question. It really comes down to efficiency. In storage, let's say we define a superkey for an employee as maybe SSN, name, hire date. Now that definitely works for uniqueness because SSN alone is unique, but including name and hire date is redundant data. It's extra information the system still has to potentially process or store every time it needs to check for uniqueness or reference that employee. It adds overhead. And that brings us neatly to the candidate key.
Right, the candidate key has to be minimal. That's the defining feature.
Exactly. A candidate key is a minimal superkey. And minimal means it's the simplest, the smallest combination of attributes you need for uniqueness. If you try to remove any single attribute from a candidate key, it stops being unique. Poof, uniqueness gone. Now, an entity type might actually have several possible candidate keys. Maybe an employee can be uniquely identified by their SSN, or perhaps by a separate employee ID, or in some cases, maybe even a combination like name, birth date could be unique, if the business rules guarantee that pairing is always unique. From that pool of candidate keys, we then choose one to be the primary key, PK. That's the designated identifier, and we usually show it by underlining it in the ER diagram.
Okay, that clarifies keys. Now, moving from the objects themselves to how they interact, let's talk relationships. So a relationship is like an instance of an association, right? Like employee Patricia Jones works on Project Alpha. Simple enough. But how do we model those trickier situations where the same entity type participates multiple times in the same relationship, like supervising another employee?
Yes, recursive relationships. That's where we absolutely need roles and role labels. They're crucial for clarity. Imagine that supervision relationship where an employee supervises another employee. If you just draw a line looping back to the employee box, it's ambiguous. Which employee is the supervisor? Which is the subordinate? So we apply labels on the relationship line near the entity connection point, labels like supervisor and subordinate. These clarify the semantics. They tell us exactly how each employee entity is participating in that specific instance of the relationship.
Makes sense. And then there are relationship attributes. I remember these being properties that only make sense in the context of the relationship itself, not really belonging to either entity on its own.
Precisely. The classic example is the hours attribute in a works-in relationship between employee and project. Think about it. The hours worked doesn't really belong to the employee entity. That employee might work different hours on different projects. And it doesn't belong to the project entity either. That project involves many employees, each potentially working different hours. The hours attribute only makes sense. It only has meaning in the specific context of that particular employee working on that particular project. And here's a critical rule to remember. A relationship itself does not have its own key attributes. It's identified entirely through the combination of the primary keys of the entities that participate in it. ## catch constraints on relationships, cardinality and participation. KO2.
Okay, moving on to constraints. These are like the formalized business rules that we bake right into the diagram itself. They fundamentally limit the number of possible combinations of entities that can actually participate in a relationship. Let's start with cardinality ratios for binary relationships, the ones involving two entity types. These define the maximum participation, right?
That's right. Cardinality ratios tell us the maximum number of relationship instances an entity can participate in. We generally talk about 4 fundamental types for binary relationships. 1, many-to-many, MN. This is the most flexible, maybe the default starting point. An employee can work on many projects, and simultaneously a project can involve many employees. This one requires careful handling when we map it later. 2, many-to-one, N1, and one-to-many, 1N. These are essentially mirror images. They're often called functional relationships because one side functionally determines the other. For example, in a 1N relationship, like a department manages many projects, each project is managed by only one department. Knowing the project tells you the department. 3, 1-to-1, 1.1. This is the strictest constraint. For example, maybe a manager manages exactly one department, and conversely, that department is managed by exactly one manager.
And the practical importance of figuring out these ratios goes beyond just classifying the relationship, doesn't it? It really affects how we translate the design into tables later on.
Oh, absolutely. The cardinality ratio is our very first clue, our first hint about how we're going to handle placing foreign keys when we build the tables. In a 1N relationship, for instance, we know pretty much right away that we can safely embed the primary key from the one-side entity into the table for the n-side entity as a foreign key. But if we see an MN relationship, we know immediately that simple key embedding just won't work. It violates basic relational principles. That tells us we must create a separate table, a junction table, to handle that relationship.
Right, that makes sense. Speaking of things not working or failure modes, let's talk about the minimum participation. This determines whether an entity's very existence depends on being related to another entity.
Exactly. This is the participation constraint. And there are two options here. The default, usually, is partial participation. This just means an entity can participate in the relationship, but doesn't have to. It's optional. The more restrictive constraint is total participation, which is also sometimes called existence dependency. In some notations, like Chen, this is shown with a double line connecting the entity to the relationship. Total participation means every single entity of that type must participate in at least one instance of that relationship. It's mandatory.
Can you give us a really clear example of where total participation is crucial from a business perspective?
Sure. Let's think about a system for managing employees and the departments they work in. If the relationship employee works in department has total participation specified on the employee side, that enforces some really important business rules. First, it means you literally cannot hire a new employee into the system unless you immediately assign them to an existing department. No unassigned employees allowed. Second, it means you can never just delete that employee's department record without doing something about the employee first, either reassigning them to a different department or perhaps deleting the employee record itself, depending on other rules. It forces an existential rule onto the data. The employee's existence in the system depends on being linked to a department. It makes that side of the relationship absolutely mandatory.
Wow, okay. So this combination of maximum participation, cardinality, and minimum participation, total or partial, is where the conceptual blueprint really starts dictating the integrity rules that the final database will have to enforce. It's powerful stuff.
Right, so once we've conceptually captured all these complex rules and structures, we need a way to draw it, a visual language. And because lots of different people need to understand these models, database designers, software engineers, maybe even non-technical business stakeholders, we need a common language. There are really three major notation styles that you'll see used widely in industry and academia.
Okay, so we're talking about Chen notation, crow's foot notation, and UML class diagrams. Let's start with Chen. You often see this one described as the sort of academic standard.
Yeah, Chen notation, which goes way back to Peter Chen in 1976, is probably the most visually expressive in terms of pure abstraction. Entities are drawn as rectangles, relationships are distinct diamond shapes, and attributes are ovals connected by lines to their entity or relationship. Cardinality constraints are usually shown as numbers or letters like 1, N, or M, written on the lines connecting entities to the relationship diamond. Its main strength, I think, is how it explicitly represents the relationship itself as a distinct object, that diamond. This makes it really good for illustrating more complex concepts like, say, ternary relationships involving three entities or clearly showing weak entities in their identifying relationships.
Okay, but what's the usual complaint you hear about Chen notation?
Well, it tends to be quite verbose, visually speaking. If you have a database with, say, 50 entity types and numerous relationships, the Chen diagram can become a real visual jungle, just lots and lots of shapes. So many rectangles, diamonds, ovals, and lines crisscrossing everywhere. It often sacrifices visual compactness for that conceptual rigor. It's often the notation people use when they're purely discussing the theory, maybe in a classroom setting, rather than directly preparing for implementation.
Gotcha. So then we shift gears to crow's foot notation. This one seems like you see it everywhere in industry tools and documentation.
You absolutely do. Crow's foot is really the pragmatist's choice. It's designed to be compact, visually quite intuitive, and importantly, it immediately suggests how the relational tables will likely be structured. Entities are typically just boxes, similar to Chen. But the big difference is relationships are just lines connecting the boxes. There are no diamond shapes for relationships. The type of relationship, its cardinality and participation, is entirely defined by these special forks or symbols right at the end of the line where it connects to the entity box.
Yeah, I personally find the way crow's foot handles both cardinality and participation together really instructive, especially when you're thinking ahead to implementation.
It is very direct. You read the multiplicity, meaning both minimum and maximum participation, by looking at two marks right next to each other on the line end. The inner mark, the one closer to the entity it's leaving, specifies the minimum participation. Usually a circle means 0 or optional participation, partial, and a single hash mark or vertical bar means 1 or mandatory participation, total. Then the outer mark specifies the maximum participation. A single line or hash mark means one, and the characteristic three-pronged crow's foot shape means many. So
Hmm.
if you see a notation like 0 connecting two boxes, reading from left to right, it instantly tells the developer, okay, participation is mandatory, the inner with a maximum of 1, 1 on the left side, and it's optional, the inner 0, with a maximum of many, the outer crow's foot, on the right side. This really helps fulfill that writing outcome 1, allowing clear communication of database theory directly tied to an implementation standard.
That clarity is definitely convenient. But I sometimes heard that crow's foot can struggle a bit when you try to represent some of those more complex concepts from the enhanced ER model, like, say, specialization constraints, disjoint versus overlapping. Do you find that's a limitation in practice?
It certainly can be a trade-off, yeah. Crowsfoot absolutely excels at representing standard binary relationships, 1.1, 1.n, mn, and clearly implying how keys should be mapped. But it doesn't have built-in standardized symbols to elegantly represent things like disjoint specialization hierarchies or generalization the way Chen or UML sometimes do. You often end up having to add custom text notes or maybe non-standard symbols to convey those richer semantics. And that's actually where the third notation, UML, sometimes comes into play.
Right, UML class diagrams, which isn't just for databases, it's part of a much broader software modeling language.
Exactly. In the unified modeling language, UML, what we call an entity in ER modeling is represented as a class. It's drawn as a rectangle, often with compartments inside for the class name, its attributes, and sometimes its operations or methods. Relationships between classes are called associations, shown as lines, and the multiplicity, cardinality and participation, is noted at the ends using numerical ranges, like 1 for exactly 1, 0.1 for 0, or 1 for 0, or many, 1 for 1 or more. The really big advantage of UML, especially in certain environments, is integration. If you're developing an object-oriented software application alongside your database, using UML for both means you're speaking the same modeling language. UML naturally supports advanced features like inheritance, which maps directly to specialization, generalization in ER, and aggregation composition. It helps bridge the gap between the database structure and the software's class structure, potentially avoiding tricky translation issues between different modeling paradigms.
Okay, so 3 different visual languages, each with pros and cons, but regardless of which notation we choose, Chen for theory, Crowsfoot for practical mapping, UML for software integration, the really key takeaway here is that the underlying conceptual model, the rules and structures it defines, must be robust. Because the next phase we're diving into, the logical mapping to relational tables, relies entirely on that conceptual blueprint. It needs to be a systematic, almost mechanical procedure, right? Okay, this is where the rubber really meets the road, isn't it? We're bridging that gap between the somewhat abstract conceptual model and the very strict formal structure required by the relational model. We're talking tables, columns, primary keys, foreign keys, the whole setup that becomes the direct input for writing SQL data definition language DDL commands like create table.
Mhm.
And you said this conversion has to be systematic. Why is that so important? Why can't we just sort of eyeball it?
Well, eyeballing it is how you end up losing critical information or introducing errors. The whole point of the careful conceptual modeling is to capture all the business rules and constraints. If the mapping process isn't systematic, isn't repeatable, you risk forgetting to map a relationship correctly, or missing a foreign key, or misinterpreting a participation constraint. That undermines the entire design. This process directly addresses skill outcome 2, building normalized schemas from business scenarios captured in the ERD. We use a standardized step-by-step algorithm, typically 7 steps, to ensure every single component of the ER diagram is accurately represented in the relational schema. To make this concrete, let's consistently use the good old company database example, with its employees, departments, and projects to illustrate how each mapping rule works.
Sounds good. Okay, let's start with step 1, mapping regular entity types. This seems like the most straightforward one.
It is, thankfully. It's
Yeah.
simple but necessary. The rule is, each regular or strong entity type E in your ERD becomes its own relation. R or ln, which is just the formal term for a table in the relational schema. All the simple attributes of E become columns in the table R. And the primary key that you identified for the entity type E becomes the primary key of the table R. So our employee entity type simply becomes an employee table, maybe using SSN or perhaps a generated employee ID as its primary key column. All the other attributes like name, salary, birth date become other columns in that table. Easy enough.
Okay, step 1 done. Now step 2, mapping weak entity types. These were the ones that rely on an owner entity for their identification, right?
Exactly. Weak entities, remember, can't exist or be uniquely identified without their corresponding owner entity, which is related via an identifying relationship. So the rule is, The weak entity type WA also becomes a new relation in table R. But crucially, we must include the primary key of the owner entity, let's call it E, as a foreign key in the new table R for the weak entity. And the primary key of this new table R is then the combination of two things. The foreign key we just brought over from the owner entity, plus the weak entity's own partial key, the attribute asset that make it unique within the context of its owner.
Okay, let's use that dependent entity type example, which is weak and owned by employee via SSN. How does that map?
Right, so we create a dependent table. It will include the dependent's own attributes, like perhaps dependent name, sex, birth date, relationship. Now, because dependent is weak and identified by employee, we must bring the primary key of employee, let's say it's SSN, into the dependent table. We'll probably rename it slightly for clarity, maybe call it ESSN, employee SSN, and mark it as a foreign key referencing the employee table's SSN column. The partial key of dependent was dependent name, assuming a dependent's name is unique for a given employee. Therefore, the composite primary key for the dependent table becomes the combination, ESSN dependent name. This structure correctly ensures that a dependent named John Smith is only unique when linked to a specific employee via their ESSN.
Got it. That composite key makes sense. Okay, moving on. Step 3, mapping binary 1.1 relationship types. You mentioned earlier we typically try to avoid creating a whole new table just for these relationships as possible.
That's generally the preferred approach for 1.1, yes. We use what's often called the foreign key approach. The basic idea is choose one of the two relations involved in the 1.1 relationship, let's call it S, and include the primary key of the other relation, T, as a foreign key in S. You also include any attributes of the 1.1 relationship itself as additional columns in S. But there's an important optimization guideline here, driven by minimizing NUL values.
All right, you mentioned minimizing NULs before. Why is that such a big deal here? If we just picked one of the tables randomly, say the one with partial participation, the foreign key would just be NUL sometimes. The system would still work, wouldn't it?
It would function technically, yes, but at a potential cost to efficiency and data clarity. NUL values, while seeming empty, still consume some storage space. More importantly, they can complicate queries. You often have to explicitly handle IS NLL or IS not NLL conditions, and sometimes make constraint checking a bit less straightforward. So the optimization rule is, if one side of the 1.1 relationship has total participation, meaning every entity on that side must be in the relationship, while the other side has partial participation, it's generally better to choose the entity type with total participation to be the relation S where you embed the foreign key. Why? Because if you embed the FK in the table with total participation, you guarantee that the foreign key column will never be NLL, since every entity instance must be related. If you did it the other way around, embedding the FK in the table with partial participation, you'd potentially end up with many rows having NLL values in that FK column, leading to data sparsity and potentially impacting query performance, especially on large tables.
Okay, that makes practical sense. So using our example of the manager's relationship between employee and department, which is 1.1, let's assume every department must have exactly one manager, total participation for department, but not every employee is a manager, partial participation for employee. Following the optimization rule, we choose department as relation S. We then embed the employee primary key, let's say SSN, maybe renamed conventionally, into the department table as a foreign key. And we'd also put any relationship attributes, like maybe Melgi start date, into the department table as well. Efficiency achieved, no unnecessary NLLs, and that Melgi Scanwam.
Precisely. That's the optimal mapping for that 1.1 scenario. Now, step 4, mapping binary 1 to n relationship types. These are probably the most common type of relationship you encounter. They are very common, yes. And the mapping rule here is quite deterministic, thankfully. You first identify the relation, table let's call it S, that represents the entity type on the n side, the many side of the one-dat relationship. Then you simply include the primary key of the one-side relation, table T, as a foreign key in table S. Any simple attributes belonging to the 1.n relationship itself are also included as additional columns in table S, the n-side table.
Okay, let's use the works for relationship, which is 1 to n from department one side to employee n side. So employee is our relation S, the n side.
Correct. So following the rule, we take the primary key of the one-side relation department, which is D number, the department number, and we include it as a foreign key column in the n-side relation, employee. We might rename it for clarity within the employee table, perhaps calling it DNO. This DNO column in the employee table is marked as a foreign key, referencing the DN number column in the department table. This structure directly enforces the business rule. Every employee works for exactly one department, as implied by the 1N, and it links each employee record directly back to their corresponding department record.
Straightforward enough. But now we get to the one that always requires a bit more thought. Step 5, Mapping binary MN relationship types. You said earlier this is where simple key embedding just fails.
Yes, MN, many-to-many, is fundamentally different. Let's think why embedding fails. If we have works in between employee and project, MN, and we try to embed the project's primary key, P&O, into the employee table, well, an employee can work on many projects. So we'd somehow have to store a list of P&Os in a single column for that employee. That immediately violates a fundamental rule of the relational model, the requirement for atomic values in each column cell. You can't store lists or repeating groups within a single field. It breaks first normal form, 1NF, which we'll likely cover in more detail later. And if we tried the reverse, putting multiple employee SSNs into the project table, we hit the exact same problem. So MN relationships fundamentally require us to create a new separate relation table S just to represent the relationship itself. This is often called a junction table, or sometimes a bridge table, or cross-reference table.
Okay, so for our worksin example, MN, between employee and project, we create a new table. Let's call it worksin. What's the structure of this new table? What columns does it need?
The structure is well defined. This new table S, our worksin table, is created primarily with the primary keys of both participating entity relations included as foreign keys. So the worksin table will contain the primary key of employee, let's use ESSN as a foreign key referencing employee SSN, and the primary key of project, P&O, as a foreign key referencing project P number. Now, crucially, these two foreign keys, ESN and O, together usually form the composite primary key of this new worksin table. This composite key ensures that the table tracks unique pairings of employees and projects. It prevents recording the same employee working on the same project multiple times, unless the PK definition includes other attributes. And finally, any attributes that belong to the MN relationship itself, like the hours attribute in our example, become additional non-key columns in this new worksin table.
Right, so that junction table elegantly resolves the MN complexity by breaking it down to two 1N relationships, effectively pointing to the junction table. Okay, nearly there. Step 6, mapping multi-valued attributes. These also seem to violate that atomicity rule you mentioned, similar to trying to embed keys in M.
Exactly the same principle applies. Remember attributes like, say, locations for a department entity type, where a single department might have multiple office locations. If we tried to store Houston, Dallas, Austin, all in one location's column in the department table, we'd violate atomicity, a 1NF. So the rule is, for each multi-valued attribute A, you must create a new relation table R specifically for that attribute. This new table R will include at least two columns. One column for the multi-valued attribute A itself, example a D location column to hold one location name, plus the primary key K of the owner entity type, e.g. D number from the department table, included as a foreign key. The primary key of this new relation R is typically the combination of both columns, Ka. So for our example, the primary key of the new dep locations table would be D number, D location. This ensures each location is stored atomically on its own row, linked back to the correct department, and the combination prevents listing the same location twice for the same department.
Got it. Split it out into a new table with a composite key. And finally, step 7, mapping n-ary relationship types relationships involving more than two entity types and a ternary relationship.
The approach here is very similar to mapping MN relationships. You generally can't just embed foreign keys effectively. So the rule is, you create a new relation, table S, to represent the n-ary relationship itself. This new table S must include the primary keys of all the participating entity relations as foreign keys. The primary key of this new table S is typically the combination of all these foreign keys, especially if the cardinalities are effectively NNN. This composite key represents a unique combination of the participating entities. For that supply example, sometimes used maybe a ternary relationship involving supplier, part, and project, meaning a specific supplier supplies a specific part to a specific project, you'd create a supply table. It would contain foreign keys referencing the primary keys of supplier. For example, name, part, part no proj name. Any attribute specific to the supply relationship itself, like quantity, would also go into the supply table.
Okay, that wraps up the 7 steps. That really is a systematic bridge, isn't it? It takes that potentially subjective conceptual design and transforms it into a very objective, structured relational schema. And having that correct schema is the absolute foundation for the next part, which is ensuring data integrity. This feels like it ties directly into skill outcome 3. Applying database security and optimization strategies, starting with getting the integrity right.
Absolutely. We've meticulously designed the structure using the ERD and systematically mapped it to tables. But structure alone isn't enough. Structure without rules, without enforcement, is basically useless for ensuring reliable data. The entire purpose, the reason we spend so much time defining primary keys and foreign keys in the relational schema, is to guarantee data consistency and integrity.
Right, because if we just created the tables and columns, maybe recorded the IDs from related tables, but didn't actually tell the database system to enforce those PK and FK constraints, we'd essentially just have a slightly more sophisticated spreadsheet, wouldn't we? What's the real-world danger? What happens if we, say, forget to define or enable a crucial foreign key constraint?
Oh, the consequences can range from annoying inconsistencies to absolute catastrophe, depending on the application. Imagine a hospital's database again. You have a patient's table with patient type as PK and an appointments table, which should have patient type as an FAK referencing patients. Now, suppose that foreign key constraint wasn't actually defined or enforced by the database system. Someone, maybe accidentally, deletes a patient row from the patient's table because there's no FK constraint telling the database, hey, wait, their appointment's linked to this patient. The deletion goes through. Now, you have rows in the appointments table referencing a patient type that no longer exists in the patient's table. Those appointment records have become orphan records. They point to nothing. What does that mean? Inaccurate billing, potentially serious legal risks if treatments are associated with non-existent patients, critical failures in tracking patient care history. It's a disaster waiting to happen. Keys and constraints are the database's built-in defense against this.
Wow, okay, so primary keys and foreign keys aren't just documentation aids for developers. They are active, automated defense mechanisms built right into the system's fabric.
Exactly. They serve multiple critical roles. PKs guarantee uniqueness for each entity instance row. FKs enforce referential integrity, ensuring that relationships between tables remain valid and consistent. They also play a hidden but vital role in query optimization, which is crucial for performance, especially with large datasets. When you define keys, you're giving the database's query planner crucial information about the data structure and uniqueness properties. If the planner knows that SSN is a primary key in the employee table, it knows that any query searching for a specific SSN will return at most one row. That knowledge allows the planner to choose much more efficient algorithms for finding that row, like using an index lookup directly, compared to scanning the entire table. So well-defined keys lead to faster queries.
Okay, so the relational model itself enforces certain inherent rules. I think the textbook calls them implicit constraints. What are the main types we need to be aware of?
Yeah, there are 4 fundamental types of integrity constraints inherent in the basic relational model. 1. Domain constraints. This is the most basic. It ensures that every value stored in a column actually belongs to the specified domain data type for that column. An age column defined as integer can't store text like 20. It also implies atomicity values should be indivisible, which is why we had to map out multi-valued attributes back in step 6. 2. Key constraints. Uniqueness. This enforces the uniqueness requirement of candidate keys, and most importantly, the chosen primary key. It ensures that every row, or tuple in formal terms, in a table is unique based on its primary key value. No 2 rows can have the same PK. 3. Entity integrity constraints. This is a very specific and absolute rule concerning primary keys. No component of a primary key value can be NLL. Why? Because the PK is the way to uniquely identify each row. If it were NLL, the row would lack a unique identifier, effectively losing its identity within the table and violating the core principles of the relational model. 4. Referential integrity constraints. This is the one enforced specifically through foreign keys. It dictates the relationship between a foreign key column in the referencing or child table and the primary key column it references in the reference or parent table. The rule states, the value in the FK column must either exactly match an existing PK value currently present in the parent table, or the FK value must be NULL. Being NULL is only allowed if the foreign key column itself was defined to permit NUL values, which corresponds to optional or partial participation in the relationship. A violation occurs if you try to insert an FK value that doesn't exist in the parent table's PK column.
Right, that makes sense. So the final really critical piece of maintaining integrity, especially when data changes, is defining the referential actions. This is about deciding what the database should automatically do when a user tries to delete or update a primary key value in a parent table that is currently being referenced by foreign keys in child tables. This sounds like where business rules get very directly baked into the schema's behavior.
It absolutely is. This is a high-stakes design decision because you're automating potentially irreversible actions based on the relationships. We specify these actions using on-delete and on-update clauses when defining the foreign key constraint. There are usually 3 main options. On-delete cascade, this is powerful, may be sometimes dangerous. If you delete a row in the parent table, The database system automatically deletes all corresponding rows in the child table that reference that deleted parent row via the foreign key. This can be appropriate for tightly contained relationships. For instance, if you delete a course record, it might make sense to automatically cascade delete all the associated section records for that course, assuming sections can't exist without a parent course.
Okay, Cascade sounds efficient but risky. Can you give me a clear example where using on-delete Cascade would be an absolutely terrible, catastrophic choice?
Oh, easily.
Yeah.
Imagine a financial system. You have a customer table, PK customer D, and a transactions table with customer ID as an FK. If you foolishly implement on-delete Cascade on that foreign key,
Yeah.
and then someone maybe accidentally deletes a customer record from the customer table, perhaps they typed the wrong ID or the customer closed their account, bam. The database automatically, instantly, and usually irrevocably wipes out the entire transaction history for that customer from the transactions table. That's usually illegal for auditing purposes and certainly catastrophic for the business.
Yeah.
You've just destroyed critical historical data. So in scenarios like that, you need maximum protection, not automation.
Yikes. Okay, noted. Definitely avoid Cascade on critical historical data. So what are the safer options then?
The safest, most protective option is usually on delete restrict, or its close cousin on delete no action. The behavior is often identical. This mode simply prevents the deletion of the parent row entirely if there are any existing child rows referencing it. The database throws an error, blocking the delete operation. This forces the application or the user to explicitly handle the situation first, maybe by deleting the dependent child rows manually or reassigning them to a different parent before attempting to delete the parent row again. For critical data where you absolutely cannot risk accidental loss of related information, restrict no action is often the best policy. Then there's a middle ground, on delete set null. In this case, if the parent row is deleted, the deletion is allowed to proceed. However, instead of deleting the child rows, the database automatically sets the foreign key column in those referencing child rows to null. This is only useful if two conditions are met. 1. The foreign key column in the child table must be defined to allow n-null values, and 2. It must make logical sense based on the business rules for the child entity to exist without being related to a parent entity. For instance, if an employee who manages a department is deleted, maybe you use on-delete set null on the misquarian's foreign key in the department table, indicating the department currently has no manager, assuming a department can temporarily exist without one. But again, this depends entirely on the specific business requirements. Does the child entity make sense on its own? If not, set null isn't appropriate. The choice between cascade, restrict, and set null hinges entirely on understanding the organization's specific rules and the desired behavior for data integrity.
Okay, it feels like designing the ERD and then mapping it isn't always perfectly objective then. You're constantly making choices, facing trade-offs, like deciding, should this concept be modeled as just an attribute? Or does it need to be its own entity? Or maybe it's best represented as a relationship? What are some of the common design pitfalls or mistakes that designers really need to watch out for and actively try to avoid during this phase?
That's a great point. Design is subjected to some extent driven by how the data will be used, but there are definitely principles and common mistakes. The absolute central principle, which underpins normalization theory, is avoid unnecessary redundancy. You should strive to never state the same fact twice in different places in your database structure. For example, if you model a product's vendor as both a simple text attribute within the product entity and also as a separate related vendor entity linked by relationship, you've stated the vendor information twice. Now, if that vendor changes their name, you have to remember to update it in potentially two different places. If you miss one, your database now contains conflicting information and update anomaly. This leads directly to data inconsistency. So minimizing redundancy is paramount.
Okay, avoid redundancy. What about using those more complex attribute types we saw in ER modeling, like composite or multi-valued attributes?
That's another area for careful consideration. While composite attributes, like address broken into street, city, zip, and multi-valued attributes, like multiple skills for an employee, can accurately reflect reality in the conceptual model, we need to be mindful of how they map. As we saw in the mapping steps, both composite attributes, often mapped to multiple columns, and especially multi-valued attributes, always mapped to a separate table, add complexity to the final relational schema anyway. So the advice is generally to limit the overuse of these complex attribute types directly in the ER diagram itself, especially if a simpler representation works just as well. They can clutter the conceptual model unnecessarily. If a complex piece of information, like that address structure, needs to be frequently queried on its individual components, for example, find all customers in a specific zip code, it probably should be modeled as its own separate entity type, for example, an address entity, linked by a relationship. rather than just being treated as a complex attribute within the customer entity. The use case should drive the structure. We also need to critically evaluate the use of weak entities.
While sometimes necessary, we should always ask, can we find or create a way to make this entity self-identifying with its own unique key? If so, converting it to a regular strong entity often simplifies the model and the resulting schema. Use weak entities sparingly only when truly required. Now, for really large, complex database models, think about a university system that needs to track people, but these people could be students, or they could be faculty or staff, or maybe even alumni, and each subgroup has specific attributes and relationships. The basic ER model sometimes falls short. That's where we introduce concepts from the Enhanced Entity Relationship, ER model, specifically to handle inheritance-like structures.
Okay, let's start with specialization. That sounds like breaking things down.
Exactly. Specialization is the top-down approach. You start with a general parent entity type, called the superclass, like person, and then you define specific subgroups, called subclasses, that have distinct properties or relationships. So person might specialize into student with attributes like major, GPA, and employee with attributes like salary, office number. The key idea is that the subclasses, student, employee, inherit all the attributes and relationships to the superclass, person, like name, address, birthday. When it comes time to map this specialization hierarchy to relational tables, database designers face a significant choice, often involving trade-offs. Do you use one single, potentially very wide table for the superclass, person, that includes columns for all possible subclass attributes, meaning lots of unnull values for students in the salary column and annulls for employees in the GPA column? Or do you create separate tables for each subclass, a student table, an employee table, that only hold the specific attributes for that subclass, plus a foreign key linking back to the main person table, which holds the common attributes?
Ah, okay. That definitely sounds like a performance and storage trade-off right there.
It absolutely is, and this directly relates to Knowledge Outcome 4, evaluating DBMS functions, architectures, and trade-offs. The single table approach, one big person table, might be simpler for queries that need only the common attributes, but it can waste a lot of storage space with all those NLL values, potentially making table scans slower. The multiple table approach, separate person, student, employee tables, is generally cleaner, avoids NLLs for non-applicable attributes, and can be faster for queries focused only on a specific subtype, like finding all students with a GPA above 3.5. However, if you need to retrieve all information about a person who is both a student and an employee, if overlapping is allowed, you'd need to perform joins between these tables, which adds complexity to the query.
Okay. And generalization is basically the reverse process.
Precisely. Generalization is the bottom-up approach. You look at several existing entity types, say car and truck, identify that they share many common features like vehicle ID, make, model, year, and then you create a single higher-level superclass, like vehicle, to contain those common attributes and relationships. Car and truck then become subclasses of vehicle. We also apply important constraints to these specialization generalization hierarchies. A key one is disjoint versus overlapping. A disjoint constraint means an entity from the superclass can belong to, at most, one of the subclasses. For example, an employee is either hourly or salaried, but not both. An overlapping constraint allows an entity to belong to multiple subclasses simultaneously. e.g., a person might be both a student and an employee at the university. This choice drastically affects the mapping strategy and business rule enforcement. Hashtag the normalization versus denormalization trade-off.
Right. This leads us perfectly into the final big topic, that constant battle, that tension every database architect or designer eventually faces between the theoretical purity of normalization and the practical demands of performance optimization.
Yes, the normalization versus denormalization debate. It's fundamental. Normalization, as we've hinted, is really the academic ideal, the process derived from relational theory. Its primary goal is to eliminate data redundancy and avoid those update, insertion, and deletion anomalies we discussed. We achieve this by following a series of normal forms, like first normal form 1NF, second 2NF, third 3NF, Boy Scout BCNF, and so on. Each normal form imposes stricter rules to break down data into smaller, more focused tables, ensuring that facts are stored only once. This maximizes data consistency and integrity. If we need to update a department's name in a properly normalized schema, say to 3NF, we only need to change it in one single row in the department table.
Okay, so normalization sounds great for data integrity and consistency, but the big downside, as you mentioned with the ER mapping, is often the impact on read performance, right?
Exactly, that's the trade-off. When your data is spread across many small, highly specialized tables, which is the result of high levels of normalization, retrieving a comprehensive view of information, say, getting a customer's full order history along with their shipping addresses and recent payment methods, often requires the database to perform complex joins across multiple tables. For small databases, this might not be noticeable, but as your data scales up to millions or even billions of rows, these multi-table joins can become extremely computationally expensive and time-consuming. This can significantly slow down read operations, making applications or reports feel sluggish.
So that's where denormalization comes in as a sort of strategic compromise.
Precisely. Denormalization is the conscious, deliberate decision to introduce a controlled amount of redundancy back into the database design, specifically to improve read performance. This might involve combining two tables that are very frequently joined together back into a single table, even if it violates, say, 3NF. Or it might involve duplicating a commonly needed piece of information, like maybe storing the customer's name directly in the orders table, even though it also exists in the customer's table, just to avoid having to join to the customer's table every time you query orders. This is very common in systems designed for heavy read loads, like data warehouses or analytical databases, where write operations, updates, inserts, deletes, might be relatively infrequent, but fast querying and reporting are paramount. Reducing the number of joins needed for common queries can drastically speed things up.
But doesn't that just reintroduce the risk of those update anomalies and data inconsistencies that we tried so hard to eliminate with normalization in the first place?
It absolutely does. That's the inherent risk, the downside of denormalization. If you store the customer's name in both the customer's table and the orders table, and the customer changes their name, you now must ensure that the update happens correctly and consistently in both places. If you miss one, your database is inconsistent again. So denormalization often shifts the burden of maintaining consistency from the database structure itself to the application logic, or requires using complex database triggers or stored procedures to manage the redundant data automatically. It increases complexity and the potential for errors if not managed very carefully. There's a common pragmatic saying, normalize until it hurts, denormalize until it works. The hurts part refers to read performance becoming unacceptably slow due to excessive joins. The works part refers to restoring acceptable performance by introducing just enough redundancy while carefully managing the integrity risks. The final decision is always a practical one, balancing the need for data consistency against the required read performance for the specific application. Is absolute consistency the top priority, like in banking?
Or is blazing fast reporting more critical, like in business intelligence? Hashtag tag outro.
Wow, okay. That really brings us full circle and to the end of what feels like a very packed, very essential deep dive. We successfully journeyed through that entire foundational database design process. We started in the conceptual requirements phase, defining entities, attributes, relationships, constraints using ERDs, and comparing different visual notations like Chen, crow's foot, and UML.
Then we navigated through that critical logical translation phase, methodically applying the 7-step mapping algorithm to convert the conceptual model into a robust, structured relational schema tables, columns, primary keys, foreign keys, that mechanical but vital process. And finally, we really dug into the integrity enforcement phase, emphasizing why explicitly defining those primary and foreign key constraints and carefully choosing the right referential actions on delete, cascade, set, null, restrict is absolutely fundamental. It's what elevates a simple collection of data into a truly consistent, reliable, self-protecting relational database system.
So after working through all this, you should now be much better equipped to actually interpret an ER diagram, apply these data modeling techniques yourself, and really understand why the SQL DDL code you'll write to create tables and constraints looks the way it does. It all stems from these foundational concepts. Hopefully this helps solidify knowledge outcome 3.
Yeah, and stepping back, just think again about how truly foundational this design work is. Ask yourself that question. If all the databases just vanished tomorrow morning, what specific part of your daily life would break first? Would it be registering for classes, checking your bank account, logging into your email or social media, playing your saved game? And then think, why would that failure happen? Chances are it would relate directly back to something fundamental we discussed today, maybe a missing foreign key breaking a crucial link, or a violated integrity constraint causing data corruption. It really isn't magic. It's all about this structured data architecture.
That's a great reflective question. Thank you so much for joining us today for this deep dive into the core of database design. If you found this useful for your BCIS 4301 studies or just your general understanding, please do hit that follow button, maybe share it with someone else who might benefit, and don't forget to check the description for links to all the course resources and further reading.
Absolutely. Remember, behind every single login, every swipe card transaction, every online purchase, there's a database making it all possible. Until next time, keep exploring the fascinating world behind the data.